Our universe is vast and ancient. We gaze out at a cosmos that stretches back some 13.8 billion years to the Big Bang. This leads us to a fundamental question. When did life first emerge in this vast universe? The early universe was a crucible of intense energy and transformation. Out of this chaotic inferno, the first elementary particles formed, eventually cooling and coalescing to form the building blocks of matter as we know it. The very atoms that make up our bodies, the oxygen we breathe, the carbon that forms the backbone of all life on Earth, were forged in the hearts of the first stars. To understand how early life could have emerged, we must first journey back to the beginning, to the formation of the first stars, and the creation of the elements that make up everything we know. And yet, the universe is full of surprises. In the aftermath of the Big Bang, the universe was filled with hydrogen and helium, the two lightest elements. These elements, while fundamental to the universe's structure, are not sufficient for the formation of life as we know it. Life requires a rich tapestry of heavier elements such as carbon, oxygen, nitrogen, and phosphorus. The first stars were colossal giants, far larger and hotter than our own sun. Deep within their cores, under unimaginable temperatures and pressures, hydrogen atoms fused to form helium, releasing enormous amounts of energy in the process. As these massive stars exhausted their hydrogen fuel, they began to fuse helium into even heavier elements, carbon, oxygen, nitrogen, and so on, all the way up to iron. These elements, forged in the heart of dying stars, became the building blocks for future generations of stars, planets, and ultimately, life itself. When these first stars reached the end of their lives, they exploded in spectacular supernovas. These cataclysmic events scattered the newly formed elements far and wide, seeding the interstellar medium with the ingredients for life. The death throes of stars not only provided the raw materials for life, but also set the stage for the formation of planets. The expanding shock waves from supernovae compressed surrounding clouds of gas and dust, triggering the birth of new stellar systems. Within these swirling clouds, gravity drew matter together, causing it to clump and spin. At the centers of these collapsing clouds, new stars ignited, their intense radiation illuminating the surrounding disks of gas and dust. Within these disks, a ballet of collisions and gravitational interactions unfolded. Over millions of years, these aggregates grew into planetesimals, the building blocks of planets. From microscopic dust grains to planet-sized bodies, the universe seeks structure and complexity. This era of star and planet formation marked a turning point in the universe's history. Life, in all its wondrous diversity, shares some common ingredients. Liquid water, a universal solvent, is essential for life as we know it. Its unique properties allow for the transport of nutrients, the facilitation of chemical reactions, and the creation of a stable environment within cells. In addition to water, life requires a source of energy. On Earth, the primary source of energy for most life is sunlight. Photosynthetic organisms capture sunlight and convert it into chemical energy, forming the base of the food chain. However, life is resourceful and can exploit other energy sources, such as geothermal heat or chemical gradients, as seen in extremophile organisms. The final ingredient in the recipe for life is a stable environment. While life on Earth exhibits remarkable resilience and adaptability, there are limits to what it can withstand. The early universe was a turbulent and chaotic place. Supernovae explosions were commonplace, bathing surrounding space in intense radiation. Black holes, remnants of collapsed stars, lurked within galaxies, their immense gravity warping space and time. Collisions between galaxies were frequent, triggering bursts of star formation and further enriching the interstellar medium with heavy elements. In such a dynamic and energetic environment, it's easy to assume that life would be impossible. The constant bombardment of radiation, the extreme temperatures, and the volatile nature of young planetary systems seem to paint a bleak picture for the emergence of life. And yet, life is tenacious. On Earth, we find organisms thriving in environments that seem utterly inhospitable, from the extreme heat of hydrothermal vents to the frigid depths of the polar ice caps. These extremophiles demonstrate the remarkable adaptability of life and suggest that it might find a foothold even in the most challenging environments. The early universe, while seemingly hostile, might have harbored pockets of stability where life could gain a foothold. The vast distances between stars and planets present a formidable obstacle to the spread of life. This has led some scientists to propose the Panspermia hypothesis, which suggests that life could be distributed throughout the universe by asteroids, comets, or even interstellar dust particles. The idea is that these cosmic voyagers could act as accidental arcs, carrying microorganisms from one planetary system to another. These microorganisms, embedded within rocks or ice, could potentially survive the harsh conditions of space, shielded from radiation and extreme temperatures. Upon impact with a suitable planet, they could then be released, potentially seeding life in a new world. Organic molecules, the building blocks of life, have been found in meteorites, suggesting that the raw materials for life are present in space. If panspermia is a viable mechanism for the spread of life, it raises the intriguing possibility that life on Earth may not have originated here but was instead delivered from another planet or even another galaxy. When we look up at the night sky, we see a dazzling array of stars, each a potential sun with its own family of planets. Recent discoveries have revealed that planets are incredibly common in the universe, with many stars hosting multiple planets. With billions of stars in our galaxy alone, and countless galaxies beyond, the sheer number of potential planets is staggering. Many of these planets likely reside within the habitable zones of their stars, where temperatures are suitable for liquid water to exist on their surfaces. If even a tiny fraction of these planets harbor life, the universe could be teeming with it. The diversity of planetary systems is equally astounding. This diversity suggests that life, if it exists elsewhere, could take on forms far stranger and more wonderful than we can imagine. The question of whether we are alone in the universe is one of the most profound in science. While we have yet to find definitive evidence of life beyond Earth, the possibility remains open. The ingredients for life are widespread throughout the universe. Organic molecules have been found in interstellar clouds, comets, and meteorites. Mars may have had rivers and oceans, and moons like Europa and Enceladus have subsurface oceans. With billions of stars and planets, the odds of life elsewhere seem probable. Even if life is rare, the number of potential sites suggests we are unlikely to be alone. The search for life is a testament to our curiosity and desire to understand our place in the cosmos. The quest to understand the origins of life in the universe is intimately connected to our search for our earliest ancestors here on Earth. By studying the fossil record and analyzing the genetic makeup of modern organisms, scientists are piecing together the history of life on our planet, tracing it back to its earliest beginnings. The first life on Earth emerged in the primordial oceans, billions of years ago. These early life forms were simple, single-celled organisms, but they possessed the remarkable ability to replicate themselves and pass on their genetic information to future generations. Over time, life diversified and evolved, giving rise to more complex organisms, eventually leading to the incredible diversity of life we see today. By understanding the conditions under which life arose on Earth, we gain valuable insights into the potential for life to exist elsewhere in the universe. If life could emerge on our planet, under conditions that were far from ideal, it stands to reason that life could also arise on other planets with similar environments. The vastness of the universe and the immense timescales involved in cosmic processes can be overwhelming to contemplate. Our planet, our solar system, even our galaxy seem insignificant against the backdrop of the cosmos. Yet this cosmic perspective can also be incredibly liberating and inspiring. It reminds us that we are part of something much larger than ourselves, connected to every other star, planet, and living organism by the shared history of the universe. The atoms in our bodies were forged in the hearts of stars. The water we drink was delivered by comets, and the very molecules that make up our DNA were likely present in the primordial soup from which life first emerged. This cosmic connection underscores the preciousness of life and the importance of preserving our planet and all its inhabitants. The question of how early life appeared in the universe captivates scientists and ignites our imaginations. While we may never know for certain when or where life first emerged, the search for answers is essential to understanding the universe and our place within it. New discoveries constantly reshape our understanding of the cosmos, revealing a universe more diverse and awe-inspiring than we imagined. From detecting exoplanets to identifying organic molecules in space, each finding brings us closer to unraveling life's origins. The search for life beyond Earth is a testament to human curiosity and our desire to explore the unknown. As we explore the cosmos, we do so with wonder and humility, knowing the universe holds countless secrets yet to be revealed.